So we are looking into a computational graph, right? Why we are talking about computational graph is TensorFlow works with computational graphs. It is not like sequential programming. So it's a computational graph. When you write a program, right, it builds a computational graph internally and tries to execute. So here a simple example of a function j that is dependent on a and b, but between j and a and b there is a function v. So if you change 1 unit in a, you need to find out how many units in j is changing, because this is the way the algorithm works, right? So when you change weights, the cost will change. So you need to know how many units of cost is changing when you change 1 unit in j, the weight. Then you accordingly can adjust the weights to reach to a global minimal error place. So to do that, we need to use a chain rule. So to find out the change in j, we need to find out the slope of the tangent, right? So this is a line, right? And we are trying to find a slope of it. So the slope is what is going to explain you the rate of change. 1 unit change, 2 units it is changing. 1 unit change, 2 units. So 1 unit change, right? It's like 2 units it is changing. Okay. So dj by dA is actually calculated by dv by dA. That's a function of a, v, and j is a function of v. So we can actually calculate derivative of j with respect to v. So dv by dA into dj by dv is going to be dj by dA. And I should have kept this dv by dA first and this one line, next. It would have been a more easier thing. So I can easily calculate derivative. See this? A is dA by dA is 1 and b is a constant. So we got 0. And here 2 into dv by dv is 2. So we multiplied those two and we got 2. Simple chain rule. Same thing I tried to show in a diagram here. This is a sigmoid neuron. When I say sigmoid neuron, the output is going to be between 0 and 1. In the yesterday's example, I actually took 0 or 1 to show you how exactly the neural network works. Okay, it is trying to adjust the weights in such a way that the output is generated. To understand that point, I actually took 0 or 1 binary classification kind of thing. But sigmoid neuron will give you a number between 0 and 1. So it takes linear combination and substitutes into sigmoid function, and this function will give you a number between 0 and 1. It will never touch 0 and 1. There is a cost function which is cross entropy, and the forward propagation is nothing but calculating this linear combination and substituting into the cost function, sigmoid activation function, and then substituting these values into cost function is forward propagation. Okay. Back propagation is nothing but adjusting the weight. Once you choose the random number, the first iteration is a random number, W and B. From next iteration onwards, it is going to be adjusted. How will it be adjusted? W1 is equal to W1 minus alpha into dj by dW1. And B is equal to B minus alpha into dj by dB. To calculate dj by dW1, when you change W1 unit, how many units in J is changing? Right? This is that derivative or slope of the tangent at that point. You need to calculate derivative of dz with respect to W, because it's a function of W's, right? Z is a function of W's, into dA by dz into dj by dA. Okay, that's the back propagation, right? W is equal to W minus alpha into dW by dz into dz by dW1 into dA by dz into dj by dA is the back propagation. There is nothing going backward, even though I denoted a back arrow here, backward arrow there, right? There is nothing going backward. It is just calculating these W's. But in a neural network, it's going to be more extensive, or more calculations will happen. Okay. So that is back propagation. For B, it is going to be dz by dB because the z is a function of B, and then dA by dz because A is a function of Z, dj by dA because J is a function of A. The calculation becomes easy. You multiply those three derivatives and you get this one, dj by dB. Okay, that part is clear, right? Is that clear? Any questions there?
Sir, is this what are the current example you are showing? Is this in one node?
Give me 1 second. Sorry, sir. Any question you said? You asked some.
Yeah. The current example what you are showing is for one node, sir?
One node, yes, and one node.
Okay.
The same thing expands when you take the neural network.
Yeah, sure.
Yeah, yesterday I actually showed you the same thing. I'm going to show you the same thing. The same, whatever is happening here in terms of back propagation and forward propagation, same thing will happen in deep learning also. If you understand one node, everything, it is like universe, right? No, if you understand an atom, the same structure is going to be followed throughout the universe. That's theory. So, right, that like that it is, right? You understand one node, the whole neural network is understood.
Sure.
So now let us jump into neural network. Anyway, you are asking that right question. So I have taken a neural network with no, I'm not sure this one. I have taken a neural network with input layer. The X1 is input layer, right? And this one is the hidden layer. Let me take a screenshot and try to explain. If this is understood, right, whole neural network is very simple, very simple. Actually, deep learning is easy when compared to the machine learning, because in machine learning, right, you will have different algorithms. You need to understand each algorithm separately, right? But deep learning is like, if you understand these concepts, right, any deep neural network is easy. Give me 1 second. So here this network is like this. Let me try to draw this here. X1, color. X1, right, input layer, right? X0, right, this is input layer. Okay, and then this Z1 and A1, right, that is the hidden layer, A1. Okay, A0 is again here A1. A0 again is what? 1, right? That's a bias term. And there is a output layer. Yeah, for output layer also I have taken this bias term. Okay, right? B and U0. Huh? No, A0. No, that's B only. Sorry, that's B only. Yeah, that's B only. Sorry, that's B. And I am getting confused. See that? And there is a cast function. There is y cap. This is B is a y cap, and there will be a cast function J. So this is the neural network, right? So to A0 nothing will go, right? To A0 nothing will go, because A0 is 1. You know, this is 1. This is 1. Always 1 it is, right? Bias term. Okay. This is the neural network. This neural network I am trying to explain. So this is one sigmoid neuron. This is another sigmoid neuron. Okay. So if you look at this part, That whole thing is A0. Okay, if you look A1. If you look at that whole thing, sorry, A1. That whole thing is B. Sorry, give me 1 second. Yeah, this whole thing is I should say like that one. Right? That is A, that is B. Okay, that's A and that's B. Okay, now when I start the neural network, I'll choose some random W0 and W1, and then some random U0 and U1. Okay, random numbers I'll choose, and I'll calculate B and calculate the cost. Now, in the next iteration, what should I do? In the next iteration, what should I do? First iteration, I chose W0 random number, W1 random number, U0 random number, U1 random number. You know, for with W0 random and W1 random, there will be some X1, right? X0 is going to be 1. I'll calculate Z1, I'll calculate A1, right? I have A1, A0 is 1. I substitute these two with the random U0, U1, calculate Z, and then substitute that into B and calculate J. That's the first forward propagation. Okay, in the back propagation, right, in the second iteration, or maybe first iteration's back propagation, I should be calculating these W's. First iteration is done. I have some cost. Now I should be calculating next W1 and next W0. What is the formula for W0? W0 is equal to W0 minus alpha into dj by dw0. Okay, that's the formula. So if you expand this, that's going to be dz1 by dw0 into da1 by dz1 into dz by da1 into db by dz into dj by db. Do you agree? Do you agree with that? Any questions there? Yes, no?
So you wrote one's number 1, which should be 0, right? For example, Z1.
No, sir, no. No, this 0, W0 and W1 both are going into Z1 only.
Oh, okay.
Right? This is the network, right? X1, A, B. Right? That is the network, actual network. So there is X0 to have a bias term, right? That is 1. Right? To have a bias term for this one, there is A0. That's it. Right? A and B are the sigmoid neurons. In A and B, there will be a linear combination and sigmoid function. Linear combination and sigmoid function. But this is the network. I should write this out. Shashiram gar, yesterday you are also confused, right? Is this clear today?
Yes, sir.
That's the network. Okay. So for D, to calculate next W1, what's the formula? W1 is equal to W1 minus alpha into derivative of dj by dW1. So here, right, this whole equation, right, this part is not going to change. Only this part will change. Right? What will change there? dz1 by dw1 into, from here it is all same. dA by dz1 dz by dA1, right? dz by dA1 into dB by dz into dj by dB, right? That is this W1, next W1, back propagation formula for W0 and W1. Can you tell me the back propagation formula for, U0? U0 is equal to U0 minus alpha into dj by du0. Can you tell me the formula for this? For this part? Can you tell me that formula? So, so when you change 1 unit in U0, right? How many units in J should be found? That is the dj by du0. Okay, right? So
dz by
du0
du0
into
and
db
dB by dz
into dj by
dB.
dB. That's it. See, the terms, number of terms are reducing. When the node is closer to output layer, right? The neuron is closer to output layer, number of calculations will reduce. If the neuron is far from the output layer, number of calculations will be more. If you take a huge network, right? This is going to be a huge calculation. Got it? But in that, right, there are common terms, right? If you in a particular layer, right, this hidden layer, if you calculate this part once, that's good. You keep that aside, you calculate this part and multiply like that. So these are all done in the as a vectorized implementation in TensorFlow and PyTorch. Okay, no need to calculate all that, but we need to understand how this calculation is happening, because there is a in between, right, there is a derivative calculated to activation function. This part, right, this part is very important. I'll talk about that, right? There is a derivative calculated to activation function. This is one activation function, this is another activation function. Okay, I'll talk about that later. But you got the gist, right? U0 is equal to U0 minus alpha into dj by du0, du1, sorry, u1 for this one, right? This part is going to be dz by du1 into db by dz into dj by db. Okay, got it? No need to understand how to calculate derivative and all, right? We have some important point that you need to understand. That's where I'm actually showing all this. Today we'll get that clarity. Can I move on?
Yes, sir. Here the z function is the linear representation, and a equal to sigmoid of z is the sigmoid function formula. Like
Yes,
what exactly the j of b comma y is
cost
is
function.
it the entropy?
Entropy function.
Okay, so entropy is applied only once at the end.
Yes,
and
that's
out.
it. That's it.
But for every neuron, the sigmoid is applied. So that's why
Yes.
we are calling
Yes.
sigmoid neurons.
The last node's responsibility is to find out the predict the whatever. Prediction is made by the last node. These internal hidden layer nodes are going to help the last node predict it correctly. Got it?
Yes.
Sir, can you go to that screen once again, the previous one, what you showed? Yeah, here. On the top, you mentioned that under the back propagation word, you put W0 equal to W0 minus alpha dj by dw0.
Yes, Sandy.
From there, the equal to you put, and then you wrote dz1 by dz1 by dw0. Is it correct?
I am calculating only this part, sir. I am calculating only this part. W0 minus alpha into this whole thing will come.
Yeah. That whole thing is nothing but dj by dw0. Is that
Content.
Yeah. Okay. So my question is, in that whole thing, the first part is dz1 by dw0.
Avunandi.
What is the next one, sir?
dA1 by dz1.
Okay. What is the next one, sir?
dz by dA1.
So there is one more. So dA1 by dZ1. After that, we need to have one more dz by dA1.
Yeah, here it is there.
Okay, maybe because it's this picture is so small. What is the difference between Z1 and Z here? Third term and second term and third term. I'm not able to follow.
This term and this one.
Z1 versus Z.
Z1 versus Z is different only. Z1 is the first terms linear combination, first nodes linear combination.
Okay.
Z is the second node linear combination, or the output nodes linear combination.
Okay, fine. Yeah, maybe because it's small in font, right? I could not see that.
Yeah.
Now it's clear.
Yeah.
It's clear, sir.
Now it is clear, right?
Yeah.
Simple, sir. To make this derivative calculation easy, we are splitting it. Right? We are taking the equation in terms of that particular variable so that we can do the derivative easily. So this equation is in terms of W1 and W0. This equation is in terms of Z1. This equation is in terms of A1. This equation is in terms of Z. This equation is in terms of B. So we are doing derivative with respect to corresponding value. If you look at this first equation, right, this one, see this dV by dA calculation is easy because it is the A and B are the terms present in V function, right? In J the terms are in terms of V, so the calculation becomes easy, and we are multiplying. Give me 1 second, I'll be back. Give me 1 second. Sorry for that. So that's the kind of how the neural network finds out the W's, right? Finds out the U's. If you have n number of layers, all the weights will be calculated like that, and then you will do forward propagation. Again, W is equal to W0 minus alpha into whatever. Like that, many iterations will happen. Like in stochastic gradient descent, or we should say stochastic gradient descent, one record at a time. If you take a batch of records at a time, a batch will happen. So we'll see how that weights thing is calculated, or that whole thing is run. So this is a neural network. See this x1, x2.
1 second. So when the back propagation starts, so the neurons from right side will be evaluated first, right? So the output neuron is first evaluated, and then it goes back.
No. It will calculate from left side only.
Okay. So the adjusting of the weights will start from the
Here only.
input layer or the first hidden layer?
Input layer only. From input layer to the whatever. Because there is no dependency, right? Yeah. Sorry, that is there. Yeah, it calculates from here because this term, right? These two terms are useful here. Got it? That's a good question. Yeah, these two terms are useful here. So if it calculates here, then it can use these, and it calculates only these. In this layer, again, this whole thing is useful. Again, this whole thing is going to be useful in the previous layer, like that it is. No? Yeah, that's a good question. It calculates from right side only. Good?
Yes.
Yeah. Okay. So let me, can I move on?
Yes, yes, sir.
Okay, thank you. So now, right, we need to understand how the weight matrices, how these values are calculated in a neural network. This is very important because if you know how the calculations are happening, you will know how much, how many input nodes should be, input record should be passed to the network and how much memory is needed. Okay. So I have taken a two-layer neural network, right? One input layer, one hidden layer, and one output layer, right? Input layer will not count. Okay, hidden layer and output layer will count. So x1, x2, x0 is bias term. So we are calculating the a1 and a2, right? Z1 we substituted that into sigmoid and we got a1. Z2 we substituted that into sigmoid, we got a2. Now we are passing these values to V, that is Z, right? Final value, whatever we calculate. Based on this, we'll make, we'll calculate the cost. Okay. So this is the network. So how the calculation happens? The calculation between the input layer and the hidden layer. See this here? Right? This is how it happens. The calculation between input layer and hidden layer. So suppose that there is a row vector like this, right? X0, X1, X2, 0, 1, 2 indicate the columns. I is the row. Okay. So ith row, right? Ith row I have taken, right? There will be n plus 1 values in a row vector because x1, x2 and so on, xn are the number of columns. Okay. We took the row as a vector. Okay. Row as a vector we have taken. Okay. So I wrote something here. Maybe afterwards you look at it. And now to calculate or to actually find out the neurons value, we need three weights because there are three values in the vector. To multiply each value, we need one weight. x0i, x1i, x2i. Three values, three weights should be multiplied. W0, W1, W2. For this node. For this node, there will be three weights. Theta 0, theta 1, theta 2. To multiply these two and produce these two equations, right? These linear equations, we can do W transpose X. Do you agree? This is W matrix and this is X matrix. If I do W transpose X for one record, I'll get the linear combinations. Do you agree? Two linear combinations in single shot.
Yes, sir, that's correct.
This is actually this is what we did in our linear regression also, right? So if you take this W and transpose it, what happens? It's going to be W0, W1, the W2, theta 0, theta 1, theta 2, right? W transpose Xi is X0, X1, X2. I'm not taking i's there, right? When you multiply this row, will multiply this column, right? It's going to be W0, X1, X0 plus W1, X1 plus W2, X2. This row, this column, right? Theta 0, X0 plus theta 1, X1 plus theta 2, X2. So these are the values we need before we substitute that into sigmoid function, right? You can actually substitute that into this. You have a vector like this, you do 1 by 1 plus e power, right? Or you do like, e power of this matrix, right? So you say this is a linear LCM, right? Linear combination matrix minus LCM, right? You will get e power values and immediately you can actually put that matrix into that whole equation there and you will get it. This is called as vectorized implementation. Okay, got it? Any questions here? Now, right, if you have 100 input values, right, x1, x2 and so on x100 we have input values, right? And then there are maybe 200 nodes in the first hidden layer, right? It is like this. The network is like this. I have a question now. So the network is like this: x0, x1, x2, and so on, x100. And there are nodes, like 200 nodes here. 200 node. This is first node and this 200 node. Right now, now this matrix, right? This is a weight matrix because we have 3 inputs and two hidden nodes, right? Between 2 neurons, we have got 3 by 2 matrix, right? So here, what is the weight matrix size? This is weight matrix, we call it as. What is the weight matrix size in this network?
100 by 200.
101 by 200.
Yeah, 101 by 200.
Yeah, right. So if you take 101 by 200, how many values they are? Like 100 into 200 is maybe something like that, right? Right, around 20,000 numbers. They are all floats. Each float is 32.
200.
Huh?
20,200.
Yeah, 20,200. Right. Each, these are all float numbers. These are all float numbers because they are decimal numbers, right? And each float number is 32 bits, 32 bits, right? So 32 bits means 8 bytes, 4 bytes, 4 bytes, right? 20,000 into 4 bytes is how much?
$80,800.
1024 megabytes, right? 78 MB, right? If you have a network with one layer that is having 100 inputs and 200 outputs, right? It's going to occupy 80 MB. Right? You need to have that calculation in mind because while designing or while we call it as network architecture, while architecting a neural network, you should have that idea of how much memory it occupies at runtime. Okay, that's the important thing here. Okay, got it? Any questions?
So here, while applying the sigmoid, so we said the e power minus of the linear combination.
Avunandi.
But you said here e power of minus of LCM, so the linear combination matrix. So is it going to put the complete matrix over there and
Yeah, we
calculate
can.
the e power of this in a single shot?
We can exponential. In NumPy we have a function called np.exp of a matrix. It will automatically calculate.
Yeah, but is it going to happen like that, or is it going to calculate individual?
No, it is going to calculate like that only. It is a vectorized implementation, we call it as. In a single shot, it will calculate all the, all the linear combinations, and then in a single shot, it will calculate exponential values, and then substitute them into 1 by 1 plus whatever. Maybe 1 plus. It is all NumPy, right? NumPy arrays have got those all capabilities. It is a, if you look at this denominator, it's a broadcasting, right? It's 1 by whatever is also broadcasting. NumPy supports broadcasting. np.exponential supports calculation of all values in a single shot, right? It is not iteration. Got it?
I'm just trying to visualize it. If
No need to visualize. Take a simple matrix and try to do np.exponential. It will give you all the exponential values of a matrix. Or you do 1 by 1 plus exponential of matrix, you will get all the values calculated automatically. NumPy has got that capability.
Yeah, could be, but if all that are calculated at once, how this U1 and U2 are going to apply?
U1 and U2 is a different thing, right? We are actually looking at only this part. Only this part we are looking at now. See that the arrow, that's the whole calculation we looked at now. One layer, right? Between two layers we looked at now. Next layer I'll show you in a moment. U and U2 we'll look at it.
Okay, let's complete and see how it goes.
So here this is U and U2. And once after calculating these values, you have the values here, right? You will have a matrix. You will have a vector of values, right? If you pass one row here, you will get a vector of 3 by 1. If you pass two rows, you will get to 3 by 2. You pass four rows, you will get 3 by 4. Batch, right? Batch you pass. I'm actually showing one record at a time. You pass one record, right? You got A0, A1, A2. A0 is 1 only, right? So A0 is 1. And U0, U1, U2 are random numbers, right? First iteration. Again, you do W transpose AI, you get the linear combination. You substitute that into 1 by 1 plus e power minus z, right? That is B value. Got it?
Yeah, that's right. But so if we apply the sigmoid for the complete matrix at once, how this A1 and A2 are calculated? In order to get this A1 and A2, the linear combinations will be, applied separately, right? Sigmoid function is applied separately on the linear.
See this, you have got this thing, right? A vector, right?
Yes.
Linear combination vector. When you substitute this into this formula, you get a vector A0, A1. Sorry, A1, A2.
Okay.
A1,
Okay.
right? And
So
you
now,
add A0, right? A0 to it, and you get a vector A0, A1, A2. And then you take use and then you do W transpose A and you substitute that into 1 by 1 plus e power minus z. In a single shot, you get that output. If there is a layer also, you get that many number of, right? So,
yeah, got it. I was thinking e power minus z of the linear matrix would be a
yeah,
single.
that's not a single number. That's a vector again. That's it.
Okay.
If it is a vector, you are passing input. It's a vector. But in this layer, right, it's going to be one number only because you combined everything and calculate one. No, when you actually multiply 3 by 1 into 1 by 1 by 3 by 1 into 1 by 3 into 3 by 1, right? W transpose, right? 1 by 3
It will be 1 by
to
1.
3 by 1, you will get one values and then you get one value only, the output.
Yes.
Okay. The next point you need to understand is if I pass one record, I got one column, one vector, right? If I pass two records, right, I'll get two here. Right? If I pass two, right, x01, x11, x21, and x02, x12, and x22, that's going to be 3 by 2 matrix it is, right? 3 by 2 matrix. If I pass four records, suppose that four records, 3 by 4 matrix it is, right? 2 by 3 into 3 by 4 is 2 by 4, right? Two output nodes, four values. For each input, there will be one value. Can you visualize that? Batch gradient descent, I am trying to explain. Can you visualize that? Should I write?
Yeah, yes, sir.
Yeah, I think tomorrow we'll cover, Monday we'll cover the activation functions. So, so here, right, what I'm saying is I passed only one record here, right? So I'm doing W transpose X. When W transpose, it is 2 by 3 into 3 by 1, right? That output is going to be 2 by 1, two rows and one column. What are those? I have shown you that, right? So when you do W transpose, that's going to be W0, W1, W2, theta 0, theta 1, theta 2, right? X is this only, right? X I have taken one row vector, okay? First row, suppose that I have taken first row only. I am passing one record at a time. That is stochastic gradient descent. Right? I am passing one record at a time. Suppose that I am passing one record at a time. So x0, 1 first record, x11 first record, second value, x2, 1, right? xn, right? When I multiply these two, W transpose xi, W transpose x1, it's going to be this row multiplies this column. I get a W0 x01 plus W1 x11 plus W2 x21, right? Theta 0 x01 plus theta 1 x11 plus theta 2 x21, right? That is the W transpose X operation, right? Linear combination I calculated. Now I substitute this into 1 by 1 plus e power minus z. I will get a1 and a2. Because I am passing a vector to this operation, numpy can calculate two values there, right? a1, a2, right? So I will append a0 here, that one value, and then pass it to the next layer, whatever it happens. Suppose that, right, this is whatever we understood before, right? Let me explain the current whatever, right? Batch gradient descent. So if you want to process 4 records at a time, right? You have 1000 records. You want to pass 4 records at a time through the network, right? So then the x is going to be like this: x01, x11, x21, x02, x12, x22, x03, x13, x23, and x04, x14, x24. Row column, this is row number, right? This is column number. The superscript in brackets is the row number, okay? Right? This is the X matrix. Okay. What is the dimensionality of it? 3 by 4. No, sorry. Yeah, 3 rows and 4 columns. Sorry, 3 by 4, right? So, will the W matrix change if you pass 4 records? Will the W matrix change? Will this W matrix change if you pass 4 records?
No.
Any questions there? Giri garu or Narayan garu?
Sir, this is clear.
The W matrix will not change, right? Because what is happening here is, for this node, you are taking one record, taking the W's, multiplying, calculating the linear combination, right? For this record, you are taking thetas and calculating the linear combination. For the second record also, you are doing the same thing. Same W's, same thetas. Okay? Same W's, same thetas. Right? This is first iteration, right? This batch will go through the whole thing and calculate error, and the back propagation will be calculated on all the 4 records. And new batch will come, new batch will come from 4th record till 8th record. Again, for all those 4 records, the weights are going to be same. It does the forward propagation, and it does the back propagation to calculate next W's. Again, you will get right, 5 to 8, sorry, right? And then 9 to 12 records will come. Again, forward propagation that for 9 to 12 records, the same W's and thetas. Got it? Got it?
Yes, sir.
Right. Now you multiply this 3 by 4 matrix with 2 W transpose X, 2 by 3 matrix. 2 by 3 matrix with 3 by 4 matrix. 2 by 3 into 3 by 4 is equal to 2 by 4 matrix, right? You get 2 nodes, 4 columns, because you passed 4 columns here. They are not columns actually, 4 rows. You get for each row there will be 2 activation values. For each row there will be 2 activation values. When you passed one row, you got 2 activation values. When you pass 4 rows, you should get 4 activation values, right? For first record, for second record, right? For third record, for fourth record. Got it? When you pass this, right, you get this 4, right? This kind of, right, columns, 4 columns will come. Got it? Got it? No?
Yes.
Yes.
Good.
And
So
A0
one
is
question.
added, right?
Yeah, one after the other.
Please go ahead.
Yeah. Go ahead.
Yeah. So the number of nodes in the given hidden layer that will be dependent on the number of inputs values, or that can be controlled by hyperparameter.
No. What you are thinking is there will be more activation nodes will get added, right? That's what you are thinking.
No. I got this. For each activation node, we will get the number of columns based on the number of rows we have
Inputs.
taken in the input.
Ah.
Yeah, but the number of nodes in the hidden layer, how that will be defined, sir? I mean,
Number of
nodes in the hidden layer. Let us say in this example, we
that
are
is a
taking
hyperparameter.
A1,
That's a hyperparameter again, right? We need to play with that.
Okay. Okay, so it is not dependent on the input.
No, it is
features.
dependent on the accuracy. We need to look at the model. That's the key, right? In deep learning, you can make the model as complex as possible. You can make the model as weak as possible by changing number of hidden layers, number of nodes in the layers, and all that. That we'll see.
Okay. Clear.
So in machine learning, you don't have that flexibility. There is lots of flexibility in deep learning. Only problem with deep learning is it needs huge volume of data. But transfer learning is one approach where with less amount of data also you can build models. In future, we will get give me 1 second. Give me 1 second. So in future, right, we'll get pre-trained models for every business scenario. Even with less data, also we'll be able to make good models. That's the when Satya Nadella or these guys like Sundar Pichai or Bill Gates, Elon Musk, these kind of guys are talking. They'll have a vision. Many people in the industry think that AI is not going to work. It will work. We should make it work. As an industry, we should make it work. It's a work in progress thing now, right? It's like 80% work in progress now. In 5-6 years, right, many things will change. Believe me, many things will change. We'll get lots of sophistication in AI, but we should be there in the industry and drive the industry in a way that moves towards more automation. Okay, so we'll see what I'm actually talking about. You'll understand in maybe a couple of days. Okay, so transfer learning is simple. When I say transfer learning, in a neural network or a gradient descent, what's happening? You took a theta and you adjust it. You took it, you find out cost, again adjust it, find out cost, again adjust it. What are you doing? You are actually learning, right? You are actually transferring the previous learning to the next iteration, previous learning to the next iteration, right? That is in a given model, but you can actually save this model and start learning from the theta where it is left. So that is actually transfer learning. So you took a random number 100, you reach to a place where 5.6 is the weight ultimately at the end. You start the new program with 5.6 and train it. Right? It may actually move a little here and there. Maybe it will get adjusted to 6, or maybe it gets adjusted to 4. That may work in the new data or your data. That is transfer learning. We'll see that in detail, but a simple example. The gradient descent has that transfer learning capability, not just the deep learning algorithms. Okay, I may be confusing you at the end, but we'll stop here. Right, I have a meeting now, so Monday we'll look into it, and you actually try to experiment, or try to think in this, in this way, because this visualization is pretty much needed for the neural networks. When you are actually designing neural networks or trying to work with neural networks, you should have this visualization in mind. Then it becomes easy, right? It becomes easy to think, right? Cultivate this thought process. Okay, these slides are already there on the drive. So any questions? Any questions?